So now we're talking about the design structural engineering spectrum. That means how broad is our field and what are we studying right now, right? So we are talking about an engineer, which is a structural engineer here, and we're looking at what he or she is capable of doing or should be capable of doing or can do. First of all, in terms of the activity, they should be able to handle a broad range of activities. Conception, that means come up with the idea, come up with the concept, come up with the development of an idea. Analysis, to convert that, to find out what will be the impact of that idea, how will it work. Design, to convert it into buildable working detail. Then detailing, to send it to the construction site on how it will actually be built. So this is like main activities that you need to do before something can be constructed. And sometimes this is done by architects, senior people, analysis. So depending upon your job, you may specialize in one of them. If you're working in a big organization, they have separate people for that, separate people for that, separate people for that, separate people for that, different departments. So if you decide to join that department, you will be just doing detailing. You will not know what happened before that. And if you're doing the analysis, you will not know what is going to happen after that. That is typically what happens in large organizations. But small firms, few people firm, each person is required to do everything, almost, right? So you get more exposure into the overall things that need to be done. Then structures, buildings, bridges, trusses, shells, towers. So many types of structures are there to be designed. And for each type of structure, these activities need to be done, right? So maybe you will become expert in one or two of them if you work in a big organization. Small organizations typically get all kinds of projects, so you need to work in everything at the same time. Codes, design codes. Previously, it was common for people just to use a code where they live. Now it's not the case anymore. First of all, you studied here, you live in some other countries, you will be working in another country. It's very common these days because of the international mobility and projects. So you need to know more than one code. Also, even if you're working here, you might get a project from another country, which is also quite common. So we need to know or need to have the ability to work in different codes or understand them, not just one code. So you cannot just learn one code and expect to do your job. You may need to be proficient in at least 2 or 3 codes, right? Major ones. So you can now imagine all of those things, all of those structures, all of those codes. And then material. Which material do you want to be expert in? Concrete buildings, steel buildings, pre-stressed concrete buildings, or wood buildings, and so on. So just choosing the material will make you a specialist or limited. So you have to then see where is your focus, what are you going to do later. Modeling, this is about more details. What kind of models are you going to use when you do the analysis? 2D, 3D, finite element, so on. Analysis, what analysis capabilities do you have? Linear, non-linear, dynamic, large displacement, and so on, right? And what kind of solutions and other things you can use. So this is more details than going down into your special knowledge areas. But the point that this slide is trying to make is to give you an idea that this is a very broad spectrum that engineers are working or can work in. And now this course is going to be about hopefully all of that, analysis and design mostly, but conception, detailing also of buildings, and most likely we will be using the American and to some extent British codes out of that, and we are using concrete, right? And we are going to use full finite element methods. We are going to use linear, non-linear, and dynamic analysis. So you can see that we are covering a broad things out of that for a particular project type, right? This is a typical activities in a design office, the way it is organized, so you can see your role, where your role will be. This is the structural engineer, the black gray box, conception, analysis, design, detailing, and also costing. And then the structural engineers are doing all of that. And if you're a one-man company, then you need to do other things also, right? Or two-man company is very common in engineering, that you make your own company and then you do all of that by yourself. Another issue that has faced our profession is that we have traditionally been trained or thinking about each step as one step at a time, like a process. From conception we go to modeling, from modeling we go to design to detailing, design to drafting and costing, and we finish the project. But it never happens like that. It almost never happens like that. Why not? It is supposed to happen like this. But real world, it doesn't happen like that. Changes. People keep on changing their mind. Conditions change at site. You finished everything and the costing became too high. So now you have to go back and change your concept and start changing things, right? On the site, some condition changed and you need to change your design and you need to check your analysis. So these steps that they're supposed to go like this, they normally not go like this. So you have to go up and down, up and down. Now the idea is to integrated design process. That means you think about the entire thing at the same time, right? You have the ability to jump from one to the other without doing the steps in between. For example, you get a project and you should be able to somehow come up with the costing before doing the design, right? So that kind of thinking and that kind of approach can be developed gradually when we gain the knowledge, and also some computer systems help us to do that. So we can quickly do some preliminary analysis, preliminary design, and then go up and down. Singapore is leader in this kind of thing because they have by law asked everybody, structural engineers, contractors, architects, officials, electrical engineers, mechanical, everyone to work off the same files, same model. So if you change something, it changes. So there's only one model. It is the technology, as you might, is called BIM, Building Information Modeling. So building information modeling is an environment in which you do this integrated manner. Everybody is working on the same model connected to the internet. So you only have one, there's no confusion on whose drawings are to be followed. There's only one set of model. There's a complete 3D model and everybody shares information across. So everybody just puts in their information, whatever they have, and it becomes integrated fully. So, but that is only possible if everybody agrees to do this. And normally everybody does not agree to do this, but Singapore can force everybody to do this because it's a small country and they have very strict laws. Other industry is following using BIM. Traditionally, we do this. Architectural functional plans, structural system. So if you get a building design, this is what you will typically do. First of all, the architect will send you the functional plan, just line diagram. Then from that, you will develop the structural system. They will ask you, what structural system do you want to use here? Is it going to be, we will talk about various options, but you need to select the structural system here. After that selection, you will need trial sections. See, one of the problems in structural engineering we have now is that before we can do the analysis and modeling, we already need to know the sizes. So column size is an input for the analysis, while the purpose of the analysis and design should be to give me the column size. But it needs that as an input. Without that, analysis cannot work. So because analysis works on the model of a structure. So the model of a structure needs the sizes already, material, everything is needed before you can model it. So you need these trial sections to be done properly. Then you go to modeling. From modeling we go to analysis. From analysis you go to member design. If member design is okay, you go to connection and other details and you finalize the design. Or if not okay, you go back, change sections, trial section to new sections, model again and repeat until you are fine, and then you move out of this loop. So that is the typical process that you will follow for your building design. So that is called conception design, this is called modeling analysis, that is called design and detailing. So basically three main key portions of the activities that we need to do for the overall design. So this is a little bit more details of the same steps that I mentioned before. It will give you an idea, pre-design, what you have to consider, and then site analysis. This is to be done sometimes by the architects, but also engineers are involved. And the preliminary design phase, what are the things that you need to do, and you need to read this, okay, to understand what each phase is doing. Basically, in preliminary design, we have to estimate the sizes, location of the columns, system, what system we are going to use, and then based on that, then we do the final design. Pre-design, we need to look at what are the primary materials to be used, design codes to be used, what are the constraints, what are the limits, what do the client want, something like that. So we understand the project first, right? Based on those constraints, then we develop the preliminary design. Computer applications in structural engineering. I developed this long time ago, and strangely enough, this has not changed for the last 5, 6, 7, 8 years. That means at that time we found that a major portion of the computer use is in an analysis. Still is the same case. Most people use the computers for analysis, except for countries like Hong Kong and Singapore, where now things are a bit different. They use it more for everything because of the BIM coming in, right? But typically we use the computers a lot for analysis, then for design, some for detailing, and other activities. Not so much for conception. This is a human activity, right? We think how to do stuff. Now, as I was telling you, what should ideally happen is this, that you have the load effects, you have the requirements, you have the constraints, and somehow this black box should give you member sizes, material specification, reinforcement, and detail. So, structural design, first of all, we idealize our structure into some form, and then we estimate the loads, then we do the analysis, and then design the sections and reinforcement beams and so on, and then production and arrangement of details, drawings and bar schedules and so on. Now, this is very interesting. Idealization and estimation and analysis. Which means that for us to be able to analyze a building, we need to do two very, very important steps before that. Idealization. That means convert the real structure into a model which we can feed into the analysis process. Could be manual, could be computer, doesn't matter. Normally, our analysis process is this, right? Does the real structure look like this ever? Have you seen any structure which has that? So which means this idealization is the first problem. right, in our process. What if this column was, so now if the real structure, let's say it was like this, and it had footings like this, and the soil here somewhere here. So this is more or less real, kind of, right? And then you converted that into that. But what if the columns were very big, like this? One column was big, one was small, and the foundation was like this, and then it had piles in it, like this, and one. How would this idealization differ from the previous one? Right? So we need to see how the actual structure is going to be made, and what is the closest idealization that we will use to represent that. Obviously the two are different now, right? And the results will not match or between the two, because real structure are so different, but our idealization is the same. So we have a problem there. So the ability to idealize the structures properly is a major skill that we need. How to be able to convert the real structure into a model that we will analyze. That's problem number one. And we may lose a lot of accuracy there. Second problem is estimation of the load. Estimation. We will almost never know the real loads. Like here, what is the load, light load now on this room? What if we have more class here? What we remove all the desks and we have a gathering or a meeting, right? So real light loads we will never know. Design light load is something else. Real load is something completely different. Earthquake. We can only know what the earthquake was after it has occurred, not before that. So how can we design for an earthquake which has never occurred yet? We can only know the wind storms, velocity and pressure after it has occurred. But how can we know before that what earthquake we should design for, what wind we should design for? So estimation is there. So how good is your estimation will affect. So estimation, analysis. Now when we come to analysis, we want to be very, very refined. We want to do the software, we want to go to the second, third decimal, 7 decimal accuracy we are looking at. Even though our input may be very wrong. So this accuracy here is not going to help improve the lack of accuracy that we made here. So that means the whole process needs to be realistically accurate, right? Not just focus. Most engineers, unfortunately, researchers, many people focus on this too much. Because this they can see, computer programs and analysis and numbers, they cannot see the errors of estimation here clearly, right? So anyway, we will talk more about that. And then design of the section and reinforcement, how to convert this analysis to the design. For example, in that case, one column may be getting a little bit more moment than the other column. But you will put the same reinforcement in both of them. You will design one column and then put the same reinforcement in a number of similar columns, because you cannot design every column to be different. In any case, the minimum number of bars you can put in a column are 4. You cannot put 3.5. It has to be 4 or 6, not even 5. So that means there is a loss of your analysis results going into design. Whatever number you got, you cannot really design for that. It has to be something else. So that means there's going to be another inaccuracy created when you convert the analysis into design and then detailing. On the side, you may want to construct every column to be different size because loading may be different. Every floor to be different column size because the loading is changing in a multi-story building, but nobody will allow you to do that. The contractor will say, or an architect will say, no, for the whole building 40-story, I don't want to change column size. So where is your design then? Because your design is saying that every column has a different load, right? So all of this, those decisions make a lot of difference. And then finally, in terms of the construction. So we have to design considering the overall impact of your decisions everywhere, right? Structural analysis can be based on rigorous analysis theories, that means mathematics, right? It can be based on semi-analytical, semi-numerical solutions, that means partly you analyze something using calculation, partly based on experience, observation, test results, previous knowledge. It could be used on rigorous numerical solutions, that means detailed, very, very detailed finite element and numerical analysis. Or it could be based on simplified numerical and empirical solutions. Or it could be just a specified design procedure. You could be given an example, a handbook, and a procedure which says to design a beam, follow these 7 steps. And you just follow those steps. Everything is given to you. Tables are given, more equations are given, and you don't care where they came from, what is the background, what is the impact, you just follow them blindly. That's what many engineers will be doing. Follow the design guidelines, design codes blindly, right? This is the minimal level, but it can only work for simple things which have been done a lot, like a simply supported beam, for example. Anything complicated than that involves some analysis. It could be here, or, so this one is out. Rigorous analytical theories, very difficult to follow. Mathematics is not going to help us that much. This has been used quite a bit, and these days most people are using here rigorous numerical solutions, detailed computer modeling, as detailed as you can get. Combine that with this one together. But in our class, we will be focusing primarily on very detailed, as detailed as we can do, rigorous numerical solutions. Okay? So, kind of the best thing we can do right now. We should be concentrating on that. Another important thing to remember is the difference between analysis and design. This is very important as we go to the next phases. Analysis is universal, as I told you in the last class also. Bending moment is bending moment, no matter where you are. A frame is a frame, no matter where you are, right? So analysis of a structural system is universal. It does not depend on any location, code, not even material so much. As long as we're doing a proper modeling, analysis is more or less universal. Design is not universal. Design will depend on material, very much, totally different. Concrete and steel design, totally different. You have, last time we have seen quite a bit, even reinforced concrete and pre-stressed concrete design, people treat it differently. So we tried to integrate some of those last time. Design codes could be very different. Design approach, working stress, ultimate strength could be different. Structural members, beams, columns, slabs, footings, they all have different design procedures. For the analysis, it doesn't matter. We can model them in a similar manner, finite element. Local construction techniques and practices will also affect what you design, right? Is it going to be top-down, and it is going to be, do we have the skills to do some slip forming or not? So the construction practice will also affect your design, and a lot of output is needed. So structural design step compared to structural analysis step are two completely different things. And some people are very good in analysis, some people are very good in design, right? So the output from analysis should go to the design. But in the design, you may need to choose what you're going to specialize in. Concrete, which codes and which methods and so on, right? So we will, when we select the design project, we will have to choose one of those things. So this is just to show you what I just described earlier, that Rigorous analysis is based on partial differential equations. Semi-analytical procedures are closed form with approximation. Right? From this one, you convert that into closed forms. WL squared by 8 is a solution coming from partial differential equations, but simplified for a particular condition. 5 over 384 WL4 by something EI deflection formula coming from here, but specialized for closed form for a particular condition. But that cannot be done for everything. Rigorous numerical techniques are full three-dimensional model, non-linear, inelastic, dynamic, finite element analysis. I will explain all of these to you later, what these are. Or you already know. Okay, we'll talk about that. Simplified is, instead of doing all of that, we do 2D or 3D, but we keep it linear, we keep it static, and we keep it simple. That is what a lot of engineers are trained to do. On a bachelor level, this is what you normally can do. Here, we will be doing this, of course. And then simplified procedures are equations, charts, tables, rules, and limits that we used to do when there was nothing else. We always used to carry Reynolds handbook. Every structural engineer in my time, just like you carry your laptop or whatever, we used to carry a book called Reynolds handbook. So that had solution for every possible thing. That guy over there, he had made a very comprehensive book, and every problem that you face, you just open that and you find the solution somewhere, right? So a very popular book of that time, Reynolds handbook. So now we jump from this one here. This is where we have jumped. We cannot do this anymore. This is not good enough. So now, and this is not possible because engineers don't like partial differential equations. Also, they are very limited. So we have jumped here, and then from there we can go to something like that. So this is how we normally work now. So this is our primary tools now that we will learn. The important thing that I wanted to emphasize today is the design codes and our relationship with the design codes. What is actually a code, and why do we have to follow it, and do we have to follow it? And if we don't follow it, what happens? Can we violate it? Right? Those kind of basic questions. Why they're important? Because tall buildings are one of the few structures where codes are not sufficient or codes are not good enough, right? And I will discuss why. Let me just give you a little bit background, some interesting things to know. This is the first code, they say, something like 1772 BC, something like 4,000 years ago, or around 2,307. So at that time somebody wrote clause number 229, so it's definitely part of a big code at that time. And it says, if a builder builds a house for someone and does not construct it properly, and the house which he built falls and kills its owner, then that builder should be put to death. It's very, very dangerous, severe code, no compromise, absolutely. So if you do something, if you don't do it right, you actually risk your life. So designers or builders were put at that level of responsibility so long time ago. So what we do is very critical. So we should not take our job easily. These kind of things worry you, and we are unfortunately or fortunately we are in a position or a job like that, if you work in the design, that this is the kind of codes that were there. Now of course they are less severe, but still responsibility lies with us quite a bit, and the codes are there to control that. So, but important thing that I want to emphasize is performance and consequence. Basically, that code links two things together, performance and consequence. If you don't do that, but the more interesting thing is that code did not tell the builder how to make the house. It did not say you should make the wall 30 centimeter and this thickness, that thickness, all of that was not specified by the code, because the people who wrote the code did not also know the technology wasn't there to define all of those things. They just believed the builder to be the expert and let him decide, and decide it right. If he doesn't decide right, that is the consequence. So earlier times, the entire responsibility of everything was put on the builder, who was the architect, who was also the engineer, who was also everything. Right? Just like philosopher used to be scientists and mathematicians and everything, one person. Now, of course, things have changed a lot. You can't really do that. You still can do that. Now, we are coming back to this. Let me just go forward a little bit. This is another one, law of Moses. In case you build a new house, you must also make a parapet. Look at the detail. You must also make a parapet for your roof, that you may not place blood guilt upon your house, because someone will fall from it. So this is another extreme, that they said when you make a house, you must make a parapet, so somebody goes to the roof, should not fall down, otherwise you are responsible for that person. But it did not say how high the parapet board should be. Just make it high enough so people do not fall. Now this is the catch here. Suppose they say this is from Bible, right? It's written there. So this is life safety that they're specifying. So it's a criteria specified. They did not say make the parapet 1 meter. What will happen if they said make the parapet 1 meter? Suppose the builder make the parapet 1 meter and somebody still falls down, who's maybe taller, he's then the builder can say, I followed the requirement, not my responsibility. Now it's the responsibility of the code who specified that, I just followed it, and if somebody falls down, it's not my responsibility anyway. But in such language, that doesn't happen. Responsibility still lies with the builder to estimate, yes, you should look at the owner, how tall that owner is, and will he fall down or not, how high the parapet should be, right? So those kind of finer things we need to see in the very old documents that were there. And then there's a complete change in this last century, not this last couple of centuries, in which we went from that performance-based specifications to specification-based, prescriptive-based codes. Okay? Then the codes start to tell you concrete strength should not be less than 3,000. No. Okay, we'll come to that in a minute. So this is quite an interesting evolution. Look at the code now, ACI code. So that is 2,000 years ago, 3,000 years ago. This is now, 11, last 2 years ago. And it says, include inside diameter of the bend in welded pipes recommended for stirrups and ties shall not be 4 dB. This meant 2 dB, 4 dB, 8 dB. So now they're telling you every little detail, even how much the bar bend diameter should be to do something, right? Now if you do all of that and still something goes wrong, you're not at fault. You were told to do that. You were not told that the beam should not fail in shear or it should be confined well. You were told to make a bend of this diameter, this diameter, this diameter. You followed that. That's the end of your responsibility. Correct? And this is because of the legal issues. So once you do that, the engineer has no liability anymore. They follow the code. As long as they follow the code, liability shifts to somebody else. But the problem does not go away. After we follow this one, my question is, what if I made it not 4 but 3.5 or 3.8? What is the consequence? Can somebody tell me, will it fail the structure? Will it have any impact on the structure? What if I made it not 8, 9 or 7? Where did these numbers come from? They look very nice round numbers, 2, 4, 8, right? But reality can't be like that. Reality must be continuous, changing. You cannot have everything so nicely done in reality. So that means these numbers are very arbitrary. And because they're very arbitrary, their performance is not known. Change in their values is not, the effect of the change in their values is not known. They are based on statistics, based on testing, based on other things and rounding off and making them easy to do. That creates the problem. in the way we work, because once we follow all that, we do not know what is the effect of this one on the actual building performance. Will it stand or not stand? And also we do not know that if we modify any of the parameters, what will be the consequence. So obviously strict following of the design codes is almost impossible. There will be variations. When do you accept the variations? On what grounds? What are the values or concepts that you use to do that? So all of these are unanswered questions when we do the code-based design. And then you might say, then why the codes are developed if we have all these questions? Codes are developed to guide the engineers on normal buildings in a certain range with normal loading, within that, so that engineers are not required to do all of the detailed checks and calculations. So they follow this one, they don't require to do a lot of checks, and they can simplify their work. And it should work, not it will, or it may. It should work within those constraints. That is what the experience has shown, right? So those are the basis of the code. And if you look at the buildings around the world, how many % buildings are tall? What do you guess? When I say tall, I mean, let's say more than 200 meters tall. We're talking about tall buildings. Okay, even 100 meters tall. How many buildings do you think are tall? In all the buildings in the world that are made, how many % are tall? Let's say more than 100 meters. 10%? Any other guess? 40%? Any other guess? What if I say less than 1% of 1%? Very, very few buildings qualify. Last year, I just saw the report from CTUFE. There is an organization which keeps track of all the buildings around the world. I think 500 something buildings qualify as tall around the world that were made in the whole year. And literally millions of buildings were made total, or if not million, hundreds of thousands of buildings were made. Out of that, 500 qualify to be tall, right? So for 90% of the buildings, 95% of the building, or 99% of the building, these provisions may just work fine. But we are not talking about those 90, we are talking about, this course is about the other 10%, let's say not 10%, 1%, 2% buildings that you people will be designing, right? Hopefully. And in future, this percentage may grow, right? So we have to come back and look at the codes again. And we have to look at alternate methods called performance-based design. So these are some of the shortcomings. We are saying over 90% buildings are covered which are less than 50 meters. So I brought the level down to 50 meters, not even 100 meters. So if I bring the level down to 50 meters, for which this code will be fine, maybe 95% buildings will qualify to that. So code is fine, nothing wrong with the code. Code is developed for those 95% buildings. Unfortunately, we are talking about the other 5% which the code does not really cover. So we have to challenge the code now when we talk about tall building. First thing, the traditional code, design codes, ACI, BS, whatever code you have studied or you study, we are going to challenge that code. In fact, the whole course, last time also we challenged the code. So in this course also we will say, reasons are given here. They are not developed for tall buildings taller than 50 meters. First thing, because they are developed for 95% of the building, not 5% of the building. So that's one reason. Second, prescriptive nature, no explicit check on outcome. That means they just tell you minimum spacing 4 inches or 100 millimeter, but they don't tell you what is the consequence if it is 5 or 3. Column has vertical bars and column has also ties, horizontal bars, right? Now the vertical load is carried by the vertical bars, right? Because the area of cross section. What is the function of the horizontal bars? Confinement, right? You all know that. But the code will not link the size and spacing of the horizontal bars with the capacity. There is no equation in the column capacity in the code which changes the capacity because you change the strip spacing. right? So which means the code does not make any distinction between stirrups which are 20 or 18 or 17 or 15 centimeter apart. For them, for the code, they're all the same. But we know that's not the case. So that is the kind of performance difference that we are talking about that codes do not realize. There is no explicit check on outcome of any decision that we make. But every decision that you make has a change in the outcome, final response to the structure. Permit a limited number of structural systems. This is one of the most important things. Please note down this point. Permit limited number of structural systems because the code is supposed to apply to 95% of the cases, so they do not allow you to choose the remaining 5%. They say if you want to follow this code, you can only do this thing. If you do this, it is outside the code. So you don't do this. So that means, for example, one of the most common limitation which everybody sort of knows or debates or is worried about is use of flat slab in an earthquake zone. The code will tell you that you cannot use flat slab in an earthquake zone, right? So, but now in Philippines we are doing many tall buildings in which we are using flat slab. So right away we are not following the code. Straight away. Code is saying, no, you cannot do it, we are doing it. How can we do it? Because we need to then follow a higher level of computations and prove that this is okay. To show that no, even if we use, this is still fine, even if you didn't follow the code, right? So if you want to go beyond that, we need different design methodologies which are beyond the traditional codes. And we will talk about that in this course, which is PBD, performance-based design. Some of you might have attended some seminars on that. Do not include framing systems appropriate for high-rise. They do not talk about most of the framing systems or structural systems, tubular structural systems and others. For tall buildings, they don't even talk about that in the code because they're not meant for that. So obviously. Then, this is based on elastic methods of analysis. What is elastic? You remember that, right? Linear elastic? You load it, it comes in, there is no cracking. And we have seen that concrete is not elastic, it's not linear. So obviously, if a code is based on an elastic method of analysis, straight away it is not going to be enough. Straight away. Enforces uniform detailing rules on all members. It says all beams must have the spacing of stirrups minimum 4 inches. But all beams in the structure are not equally stressed. Some beams are more important than the others. Some are secondary. Some are not even doing anything. They're just there because the architect wanted something. They're not taking any load. So if you enforce uniform detailing rules, what are we doing? We are creating members which some of them which have excess capacity, unnecessary, and some of them may be very close to capacity or even less than capacity, because we are not realizing their critical nature in the building's performance. We are just treating all the beams and all the columns same way, and that is not right. Right? Enforce unreasonable demand distribution rules. They ought to tell you this is what you should do, but reality is not like that. One of the most common rules that the codes got it wrong, now they are changing many codes because of that. They say in a tall building that if you have frame and shear wall will take 75% of the force, frame will take 25%. How do you know my building? The code doesn't know my building. The code doesn't know how many shear wall I have, where they are located. They don't know what is my column size. How can they tell me that my building and another person building another building, they will all behave like this, that 75% will go to shear wall, 25% to frame. But in reality, what we have found is sometimes the wall takes 98%, frame 2%. Sometimes wall takes 40%, frame 65%, 60%. So obviously the codes cannot, but they used to prescribe this kind of unreasonable demand distribution limits, which are not consistent with the structural response. Do not take advantage of the recent computing tools. Of course, codes are changing, and then there's also a problem. I'll come to that. But until recently, they did not take advantage of the advanced computer software, and rightly so, because not everybody has those programs, or not everybody is trained to use that program. So now the problem is opposite. So now when you look at this slide, you suddenly know that, oh, codes are useless. They have no use for me, right? But please don't believe that they are not useful for anything. They are still useful. You are still required to follow them by the law to some extent. But for tall buildings, you need to understand that there's going to be more than this one. There are going to be other documents, there are going to be other things, other techniques. And we need to understand well enough to break any of these rules. You cannot just automatically break them. Okay? So that's something that we will talk about. Some more things. One of the important things, basis of the design code, is this word. How many people know the word implicit? The difference between implicit and explicit. What does it mean, implicit? Hidden. Implicit means something which is not said, but it is meaning to be like that, right? So when I say something, but I mean something else. So the meaning is kind of hidden. It's not clearly said, but that is the meaning behind that. So codes are implicit. That means when they give you some requirements, their objective behind the scene is this one. But you cannot verify this. Number one, for earthquake especially, let's talk about earthquake or any loading for that matter. They say that resist minor earthquake without damage, which is anticipated to occur several times. So certain things, I'm not going to go into detail right now. Some things in the design code are implicitly recognized, and the code is developed to cover that somehow. But you cannot see how they are covering it. For example, the spacing of the stirrup is specified to control some damage, but you cannot see what is the effect of that damage if you change the spacing, because the code does not have any mechanism to show you that. They only have a mechanism to tell you follow 4 inches, but they don't tell you what will happen if 5 inches or 3 inches. So that is implicit, not explicit. What we need is explicit verification of change of those parameters. So what we are looking at is explicit relationship between input and output. So if something should change in the input, something must change in the output. Correct? That is what you expect in a proper system. But in the code, that's not the case. If you change something, you cannot see the effect. Like column spacing, vertical stirrup spacing, if you change it, column capacity does not change. But in reality it does. But the code will not give you any formula that will change that. You change the stirrup spacing, the shear and the moment performance of the beam will change, but we cannot see that change in the code. And that is the difference between implicit and explicit evaluation. So what we will try to do is, after we follow the basic code things, we will try to go to the explicit level using performance-based design. Okay? Designed for achievements of specified results rather than adherence to particular technologies or prescribed means. So we don't want to tell you how to do it. We just want to tell you, this is what I want, give me that. That's it. How you do it is your problem. I just want results. I don't want to tell you how to do it. That is the codes are opposite. They say, I will tell you what to do. I don't care what the results will be, or you cannot know what the results will be. So totally opposite. The codes will tell you exactly what to do, but you don't know what is the outcome of doing that. You're doing it blindly. The other extreme is they tell you, I want this, I don't care how you do it. So we are talking at performance-based engineering, which is totally different from prescribed engineering. Long time ago, not that long time ago, when you made concrete, they used to write in the specifications of the concrete. Now these days they specify concrete strength should not be, we want to go concrete strength of 3000 psi or 20 megapascal or something like that. Before that, the codes used to say concrete should be made from 1 to 4. 1 cement, 2 sand, 4 aggregate. That used to be the specification for concrete, not strength. So whether you get a strength or not, it didn't matter. As long as you put 1 cement, 2 sand and 4 aggregate, you are done. Whatever the strength is, not your problem. Then later they changed that prescriptive way of specifying concrete to performance-based specifying concrete. I want the strength. Whether you put no cement at all, I don't care. Just give me the strength. Right? Whatever you do, I don't mind. I want strength. So that is the difference between performance and prescriptive thing. So what we are doing now is performance-based engineering. That means we want to focus on the result and outcome and not the way to go there. That should be, but that is only possible if engineers are knowledgeable enough to find their way. Right? So that's what we are trying to do here, to make you knowledgeable to find that way. So performance-based design approach, how is it different? How does it work? Client, designer, independent engineer, they form a team. Some people get together, knowledgeable people get together and they decide how they are going to do it, not the code. And then they look at some guidelines. What other people are doing. Guidelines are a summation of what other groups are doing. Not codes, guidelines. They guide you, but not tell you what to do. Those are here. Peer, TBI, ATC, FEMA, there are many. These are all professional organizations, not government bodies. So they are groups of engineers who get together and they share experience and they publish some document. And then you can look at that and then you can say, okay, I like this one or I don't like this one. Okay? So they together decide how we are going to do this, what we are going to achieve. And then what to expect, how to achieve this kind of approach, knowledge, skills and tools. So what we need is knowledge, skills and tools. That is where we come in. Knowledge and skills. And tools is sort of software that you are going to have to learn and use. So combined together, you should be able to do that. Alright? Now some people are saying that performance-based design is also not enough. We should see, because first is code was saying that if you follow the code, you don't know what you will get, right? So not good. Then say performance-based design, you at least know what you will get. The question is, what if you don't get that? What is the consequence? What is the effect? Suppose you want a certain performance and you didn't get it. What do you do? Suppose a building has been made already and now you, first of all, it followed the code, but we don't know what earthquake level it can resist. Suppose we do the performance-based evaluation and we find out that it can resist an earthquake level of a certain magnitude at that location or whatever, right? Suppose the actual earthquake expected is more than that. So we know the performance, we know it's not enough, then what? Do we demolish the building? Do we take the risk? Do we fix the building? Or what? That part is the consequence of doing something or not doing something. So insurance companies, they want to insure a building. They want to know what will be the consequence of an earthquake on this building? What kind of damage can we expect, so that they can fix their insurance premium. For example, AIT, the biggest example is AIT's flood. Very lucky that AIT got flood insurance just 1 year before the flood. AIT did not have flood insurance. And for some reason, somebody came and there was no flood expected here. So AIT, somebody come and there is a certain premium you have to pay. Somebody made a wise decision and they insured AIT for flood. And next year or 2 years after that, big flood came. And we have this huge damage. So insurance company did not expect the flood to come. Nobody expected that flood to come, so they insured AIT for 500 million or whatever the number was. And the flood came. So insurance company has to pay. So they did. So insurance company lost a lot of money because AIT had just paid one premium, only 1 year, small amount, and then they have to return 500 million to AIT for the flood. So they made a wrong assessment of the risk or whatever. So insurance companies all over lost a lot of money during that flood. Right? Now the insurance companies are saying, before we insure anything, we would like to know if a flood of that level, what will be the consequences before we can insure something. Right? So consequence-based is much greater system, which requires many frameworks, many things, quite comprehensive damage probability metrics, design rehab techniques, synthetic, so many things come into that. So it's still beyond, it's a new phenomenon, right? So we are still working towards it. But just for you to know that, okay, performance-based design is not the end. Risk-based design or consequence-based engineering is the next step. These are those guidelines that I talked about. So for tall buildings, these are our guidelines. ACI code and others are fine, but we are going to work on TBI, most important book. All of these are available on the internet. So please go ahead, get your copies. They are free. Okay, what is more than that? This is what you need for tall buildings, more than what you studied in the last course. Right? First of all is story drift for occupant perception. This is number one issue or number one control or number one consideration in tall buildings. Story drift. What is drift? Has many meanings. People who sleep, they said, please don't drift away. That means don't move away. So drift, or sometimes something drifts away from you. So drift is movement from some reference point to another point. That is drift. So story drift is the movement between two stories, relative movement between two stories. And it has two components. One is a net drift between these two, and one is also a drift when we tilt the building. So we will talk about net drift and total drift. So story drift is one of the most important criteria to consider in tall building design. One of the first thing you will be checking, or most important thing you will be checking, is story drift, and there are limits to that. There are many reasons for that. Because if the story drift is small, the walls will not crack, glass will not break, people will not be hurt, because you have controlled that. And also, if the story drift is small, they will not feel the movement so much. So story drift is one of the key controls in a tall building. Second one, of course, is stability and overturning. We don't want a tall building falling down in wind or earthquake. They're so tall, you can, looks like they will fall down. Some buildings are really very, very slim, right? Stability and overturning is second important check. The building should not fall down and must be stable. Of course, very important. Axial shortening of columns. This is an interesting phenomenon. Normally, we don't care about the axial shortening. We normally can talk about the moment in the column. But for tall buildings, the building is very tall. Let's say this is a column. If you have a load here, this column, let's say it has a strain 0.001 because of the load, right? Multiply 0.001 by 200 meters. How much will that be? Quite a bit. And if two columns are not loaded equally, one column will shorten more than the other. So that means building will start to tilt or will not be straight anymore. And shear walls normally shorten less than columns. So columns will shorten more, shear wall will shorten less. So this axial shortening of column becomes a very important consideration in tall building design. Transfer girders and deep beams. These are the topics that we are going to discuss further. Transfer girders and deep beams. Transfer girders are needed because normally the building use changes. When you go to a building, any tall building, normally at the ground floor they have a big hall, they have a shopping center, they have movie theaters, they have all those kind of things, and on top of that they have a residential building or an office building. Typically, that's how tall buildings work. So there's a portion of the building is called podium. Podium normally has different use than the main tower, and tower is sitting on the podium. So when the tower comes down on the podium, on the tower may have many columns, but people don't want to see many columns in the podium. Because of that, many of those columns need to be stopped when they come to the podium. So now you can imagine a building that's a 40-story, column is coming, carrying the load, bringing the load, and it cannot go to the foundation. It must stop at the podium level. Now there you need to create a transfer system that will transfer that load from that heavily loaded column, which was supposed to go to the foundation, to other places, and then transfer the load. So you can imagine what kind of beams and system you will need to transfer those very, very heavy loads. So transfer girders and deep beams are essentially part of the tall buildings, of every tall building, and they create so many issues, challenges, problems for us to solve. Shear wall design and detailing. Shear walls are the cornerstone, key element in a tall building less than 300 meters. Beyond 300 meters, we start to rely on other systems like tubular systems and other things. But we are not doing 300 meters buildings. We are mostly talking about smaller than that. We will talk about tubular systems, so at least you know. But not a lot. So shear walls is going to be your primary friend. So you need to really learn to know shear wall very well, right? Very, very well. If you want to do a tall building, you need to know shear walls well. Okay. Constructions. So this is important. Detailing and design. Shear. Construction sequence analysis. Construction sequence analysis. Normally, when you make a model, buildings, you start to analyze the building, you make a model of a 60-story building, right? You apply the dead load to it, you apply the wind load to it, you apply the earthquake load to it. So the dead load was applied as the building was constructed, not on the day it was 60-story, right? So during that whole construction process, many things would have happened by the time the building became 60 stories. But in our conventional analysis, we assume the building was born 60-story and we start applying load to a 60-story building. But that is not how it was done. It was done on a weekly basis or a monthly basis. So the load was applied as the building was built. So that difference between the way building was built and the final building creates a difference in results. We will talk more about it. So you need to do construction sequence analysis. You need to also build your model in the same manner the real building was built. So you can estimate the effect of the construction process. Right? Construction sequence analysis. I can tell you 99.9% engineers do not either know about it or never do it. And this is one of the things that we need to do. But again, 99.9% of the engineers do not design tall buildings. So it's okay. Design for lateral loads. Obviously, we talked about that a tall building is defined as the building which has very high lateral loads or where lateral load governs. So estimating the lateral loads, applying the lateral loads, earthquake and wind and others is the key. Right? So that's going to be, and of course earthquake is going to be very important, wind is going to be very important. Seismic performance. This is different. This is different from lateral loads. Seismic performance is how the building will perform if it is hit by a strong earthquake. Example is Japan. 9.0, almost close to the maximum possible earthquake anywhere on the world. They experienced 9.2, 9.1, and not a single tall building fall down. Right? They swayed, they didn't, nothing fell down. There were some small casualties, some roofing fell down, but no building fell. You have all seen the videos of buildings moving, right? In that earthquake. If not, go back again, check. How did they do that? Seismic performance. I told you about the example of Chile. Such a big earthquake happened there. Hardly anybody got killed. Many buildings got damaged, but not enough to cause injury. Tall buildings, mostly in the city. Two-story buildings in Haiti, 200,000 people died from collapse of two-story buildings. An earthquake 500 times stronger than that hits Chile after 1 month, and not many people died because they strictly use performance-based design and seismic safety. So that is a difference between life and death. Because now these days, in future, as I mentioned, more and more tall buildings will be constructed, more and more. So that means more and more people will be living in tall buildings. So more and more safety of the seismic safety of the buildings is becoming important. Right? Now what did I press? Again? Okay. So we need to worry about this, and that is when performance-based design comes in. So these are some of the key issues that you need to remember when you're designing tall buildings, and that we will discuss in this course. All right. Other criteria: weather comfort, temperature, relative humidity. Not our business, but important. Motion control comfort criteria. This is our business. When you are living in a tall building, it should, and suppose when, okay, let me ask you, if the building is 200 meters tall, okay, 300 meters tall, let's say 300 meters tall, in a strong windstorm, how much do you think it might move at the top? 20 centimeter. Anybody else? 15 centimeter? 20 centimeter. What if I tell you 1.5 meter on each side in wind? And what if I tell you in strong earthquake it is allowed to move up to 9 meters? Yes. That is the kind of flexibility, and that is the kind of thing. Of course, 9 meters is extreme, but 1.5 meter is not extreme. It is quite normal. It is supposed to move that without any damage, without any problem, right? So we are talking. So if the building is going to move that much, we need to make sure it does not move too fast. Otherwise, the people in that will be sitting and making dizzy, and and they will be complaining. So building has to move, it's going to move, but it should not move too fast. So the acceleration of the movement has to be controlled, and there are limits on that. How many percent of G you will allow? Motion control criteria is very important, and we have to check that for wind as well as for earthquake. Other function-based criteria will come later. So tall buildings, these are the criteria. So if I drift, motion control, axial shortening, construction sequence, transfer girders, shear wall, those kind of things. So these two slides will tell you what are the key things that you need to worry about when you're designing tall buildings. Okay? This is the limit, typical values of acceleration, human motion perception. So 0.0 to 0.5% G, no perception. You cannot feel it. Then from this point to the threshold of perception. So 1.5% is the limit. After that you start to feel it, slowly. Annoying, this is annoying, very annoying, intolerable. More than 15% is intolerable. Just more than 15% is not tolerable in a building at all. Alright, so that's just about summary of the tall buildings. These are some of the references. I won't stop here.